What? No, I'm sorry. Actually, my doctor is really nasty. I was gonna say I've put it in my mouth before. Really? Sure, tell me when you're good. Is it burn? Alright, is it a new pair? Oh, okay. 53, the multiple choice. Is that what you're talking about? Okay. So 53 says if f of x equals cosine x, then the mean value theorem guarantees that somewhere between 0 and pi over 3, f prime of x equals. So remember, this is derivative, so that's IROC. Mean value theorem deals with AROC equaling IROC. So what I want to do is I want to find, if I find AROC, then I'll know that IROC must equal that somewhere, right? So we'll do AROC. AROC is just slope. So I need f of 0 and I need f of pi over 3. I was looking at FRQs for y'all this morning with these type problems. So f of 0 would be cosine 0. What's the cosine at 0? 1. What's the cosine at pi over 3? Anybody? 1/2. So now let's plug in for slope, right? I'm going to do, I'll do this one first. So 1/2 minus 1 over pi over 3 minus 0. Negative 1/2, and I'm going to multiply by the reciprocal here, 3 over pi. Negative 3 over 2 pi. That's my average rate of change, so I know that somewhere in the interval that has to equal, is that one of my choices? Yeah, A. What else on your homework? How about 54 where it's decreasing? Didn't you say you have trouble with the increasing decreasing? This is, y'all missed this one on your test a lot, the E. But not on the test. So it asks for intervals on which it's decreasing, so I'm going to do my first derivative test with my sign analysis, okay? So I need my derivative, and I don't know if this, is this a calculator? This is a calculator, but let's see. All right, so e to the anything, the derivative is e to the anything times the derivative of the anything. So 3x squared minus 12x. So since this is two things multiplied together, I can set each one to 0 to find out where it's 0, right? When does this equal 0? Well, when one of them equals 0. E to all of this mess, when will that equal 0? Never, right? You're never gonna, there's nothing you can raise it to make it 0. You can get really, really close, but you can't actually be 0. So that's not even a part of my solution. Now I can look at 3x squared minus 12x equaling 0, and I can factor that. That's a pretty easy solve. 3x times x minus 4. So I have two potential critical points here. 0 and 4. The derivative tells me what the function itself is doing. So is the derivative positive or negative when x is less than 0? Any ideas? Nobody? All right, no matter what I plug in here, this is always going to be positive, right? I'm never going to have anything. Okay, so you plug it into the derivative. Yeah, so look at your derivative, and this is where I'm testing to see. So what I want to know is if I plug in, let's say -1, if I plug -1 in here for every x, do I get a positive number or a negative number? This is going to be +3, plus that's going to be another positive. So a positive times a positive is positive. And if my derivative is positive, that tells me my function is increasing. That's that first derivative test. That's what it does. All right, so then between 0 and 4, so maybe I plug in a +1. Remember that first one's going to be positive. If I plug +1 in here, I get 3 minus 12, which is negative. When a positive times a negative is negative. And then bigger than 4, first one's still positive because there's nothing I can plug in here to make that be negative. So I don't even have to worry about that. I'm just worrying about this piece. And if I plug in something bigger than 4, that gives me a positive. So a positive times a positive is a positive, which tells me I'm increasing on that interval. So the question asked, where is my function decreasing? Well, I only see one interval where I'm decreasing, and that is from 0 to 4. By the way, was that this class or pre-cal I was talking about? Was it inclusive or exclusive? Was that y'all? Okay. Increasing, decreasing is inclusive. I did look yesterday. I don't know why I had a brain fart, but I did. Uh-huh. Continuity. Is that what we were talking? I think that's, yeah. So that would be exclusive, but the increasing, decreasing would be inclusive. Good? What else? 55. Which of the following, ooh, I forgot we did antiderivatives yesterday. Which of the following is an antiderivative of 1 over the square root of x? So I think that I will make this x to the -1/2 and try to do the backwards power property kind of thing, which remember adding 1 and then bringing this whole thing to divide by down here. So -1/2 plus 1 is 1/2. And if I divide by a 1/2, that's the same thing as multiplying by 2, right? If you divide, so if I add these together, I get 1/2, right? And if I divide that, because you want to divide by whatever this exponent is after you add, so dividing by 1/2, I would multiply by 2 instead. And then I'm going to add my c on the end. I can't forget the c. So there's my general antiderivative for that one. And I'm going to just check and make sure it works. 1/2 times 2 is 1. So I get 1x. And then subtracting 1 gives me -1/2, which does bring me back here. And so what do my choices look like here? I've got 1 over the square root of 2x cubed negative. That can't be it. I know it's got to be this, which is 2 square root of x. But I can have any constant here on the end, right? Option B is square root of x over 2. That one doesn't work because the 2's got to be in the front. Option C is the square root of x plus 5, and that one doesn't work because, again, I'm missing the 2 in front. So D is the only one that works, and it is 2 times the square root of x minus 10. And I can do that because that C can be any constant that I want it to be. So that would be a derivative. If it has more than just an x down there, so it's got like a function in the bottom, you would do natural log. Does that make sense? Or, no, because if it's just 1 over x, that would go to natural log. If you're in a situation where you can't do the power, because here I couldn't do, if I added 1, I'd get 0, and my x would go away. So if you can't do the power, look at the log. Try the power first, though. That's a good question. What else? Sure. Just one of those. A marathoner ran the 26.2 mile. New York City Marathon in 2.2 hours. Showed that at least twice the marathoner was running at exactly 11 miles per hour. So I think this is more of an explanation type problem. I don't know how they did it, but my thought would be my average rate of change here would be 26.2, which is what? Miles per hour. So my reasoning would be at some point during the race, by the mean value theorem, she had to hit 11.909 miles per hour, right? Would you agree with that? At least one time. So if she had to hit this at least one time, then think about as she's running, here she finally hits 11.09 or whatever it is, right? But then she, at some point she stops. So now I've stopped and I'm resting, right? She had to get up to 11.09 and she's got to come back down to resting over the course. So she would have to hit 11 at least 2 times through that, right? So mean value theorem tells me she had to reach this one time. And since that is more than the value they're looking, she had to hit it getting there and coming back twice. So that's more of an explanation type problem, but we would say that by the mean value theorem, she hit it 11.909 miles per hour at least once. What else? We get into the good stuff now because this is the stuff that we take everything we've learned now about derivatives and everything else, and we really just kind of connect it all together to do the things we're doing. I know that's exciting for y'all. You can give them to me when you're done. Are you done? I'll give them. Thank you. No rush. Yeah, as soon as I get through this, I'll do time work on it. You won't be here tomorrow? Oh, take me with you. Graph wise from the first derivative test, we'll see if we'll do second derivative. I really want to do second derivative test with concavity. I'm ready to get to something. I feel like we've been doing this increasing, decreasing, max min stuff for a long time. Let's see. Yeah, this is 5.3. So this is, the title of this is Connecting Derivative. This is I feel like I say this a lot now, but we've gotten to the stuff that it really starts coming together. This is a heavily, heavily tested. Like I have seen 2 of these type in FRQs on one test before. with the graphs of the derivatives and the graphs of the function. So it's pretty heavily tested. It's going to be a given FRQ for sure with your first and second derivative test. All right, let's see. I'm going to draw this the way I have it on my notes. Can y'all see the kind of places I was kind of trying to make the, these are the only ones that you might not quite see. Okay. I'll give y'all a second too. So what I really want to talk about at each one of these points is what is the derivative doing? This is the graph of F. So what I want to know is at each one of these points, what's happening with the derivative in between? What's going on? So instead of using the derivative to tell me what the graph is doing, let's look at the graph and tell what the derivative is doing. But using the same kind of logic and the same reasoning. And in fact, let's connect this with the sign chart we're used to seeing. We'll call this F prime and F, and we'll put all our same values. Closed interval. Tell me what you know about A. It's an endpoint. What else do you know? It's a local max. That's exactly right. Okay. It's an endpoint. It's a local max. So I know that A is a local max. I know that it's the left endpoint. And as I move to the right, what did I say something stupid on that video, Hope? She's smiling at me to do that. As I move to ah. You just started smiling all of a sudden. I was like, oh God, I probably did something wrong or something stupid. Okay. So between A and B, tell me what the function is doing first. Decreasing. We all agree it's decreasing. So what does that tell me about the derivative? It's increasing. So as I move, no, the derivative, negative, right? negative. Function's decreasing, so that means so to the right, I know that the derivative is negative, or starts going negative as I go that way, right? The left endpoint of the function, because it's restricted. Yes, yes. Say again. So to the right of A, because all this, I'm just describing some things about A here, making sure we understand what's going on. So it's the left endpoint, it's a local max, and to the right of that point, my derivative is negative because I'm decreasing on my graph, okay? Because between A and B, derivative is negative, right? Because this is decreasing. Now what happens, so I know this interval, this AB interval, right, is decreasing. What happens between B and C? Because I marked B and C for a reason. I mean, I marked B for a reason, but what's happening between B and C, derivative-wise? It's still decreasing, right? So my derivative is still negative. Do you agree? It may not be quite as negative here, and then it may get, some things are changing here, and that's what we're going to talk about with our second derivative test. There's something changing. Can you see how something's changing and something's different here? I'm opening up, and now I'm opening down. This is the point where I'm changing. So it's still negative because I'm still decreasing, but B is a special point here. So B it's not an extrema, but I know something's happening. But I know it's not an extrema because my derivative does not change signs. Tell me what you know about C, the local min. Why is it a local min? Derivative changes signs. Changes from negative to positive. It starts increasing there, right? What else is special about C? It's what? It's like a cusp or a corner right there, right? It's not differentiable. C's not. I can look at that and tell it's not differentiable. How can you look at it besides it coming to a sharp point right there? What does it mean to be differentiable? Exactly. The slope from the left has to be the same as the slope from the right. They have to come into that same value. So I also know that C is not differentiable. So as we were looking algebraically, remember we tested all those points, but we did not just where the derivative was 0, but also where it was not differentiable. And this is why, because look, it happens to be an extreme point here, but it's not differentiable. So if we hadn't picked up on those non-differentiable points, we might not would have picked up on that C. All right. What about D? Hold on, I messed up somewhere, didn't I? Between C and D, yeah, that's right. Between D and E, positive or negative? Negative because I'm decreasing, right? What happens at D? It's max. Local max. Why? Because the derivative changes from positive to negative this time. What else do you know about D? What do you know about the derivative at D? Horizontal tangent. Which means what? 0. Right? Horizontal tangent this way, every max or min, right? Tangent there would have slope of 0. How about E? What happens between E and F? Negative. I'm still decreasing, right? Still decreasing between here and here. E looks like another one of those special points that the derivative's not changing signs, but something is happening. Look, again, I'm opening up and opening down. It looks like that's where it's changing that, and we will talk about that soon. So other than that, E doesn't look real special to me just yet, but it will. So I won't say anything else about E. How about, other than, maybe I'll put D and E. How about F? F is an absolute min on this graph. And I'm going to say, I know it's a local min. I can't say absolute by the first derivative test, but I can say that it's a local by the, because the derivative changes from negative to positive there, right? And it's an absolute because it has the lowest function value. And if I wanted to say that, I definitely could say that. But remember that first derivative test is only going to test you for locals there. You have to plug in to find your absolutes. Anything else about F? Horizontal tangent is a 0. That's exactly right. The derivative at F would be 0. Horizontal tangent there. How about H? Oh, shame. G, how about G? G is a vertical asymptote. What does it tell me about the derivative? Anything? It's not continuous there. So if it's not continuous there, it's not differentiable, right? So there is no derivative there. So it's not, it can't be a critical point, can't have any type of extreme value, can't be extrema, it's not differentiable, it's not continuous, it's a lot of knots, right? It's, in fact, G is not even on my graph of F. Now the good one. Tell me what you know about H. It's a hole. It's also not continuous, and if it's not continuous, that tells me it's not differentiable. Can I call H a local minimum? No. Why? If I'm strictly looking at calculus wise and the first derivative test, why can I not call that a local minimum? It doesn't have a derivative. It doesn't, I can't first derivative test it if it doesn't have a derivative. So remember, to be a relative max or min, you've got to be able to, it's got to be, well, no, I can't say that because C was not differentiable. but the continuity is not going to allow me to call it. I'm going to say it's not an extrema defined by the derivative test, because it's not differentiable there. I can't show that it's 0, or I can't show that, I can't show much because of the discontinuity, not because of the derivative as much as the discontinuity. Does that make sense? The whole point of this was showing you a whole bunch of stuff that's happening. Oh, I didn't do I. I could actually put A and I kind of together too, because it's an endpoint and also a relative max. The whole point is looking at the graph of the function, you can tell a lot about the derivative. So you have to be really careful with what's given to you. Sometimes they'll give you the derivative, and you'll have to interpret a lot about the function as well as the second derivative, and sometimes they will give you the function and you have to make a lot of inference about the first and second derivatives. All right, so in a nutshell, first derivative test, we're testing for extrema, increasing, and decreasing. What time is it? I think, but I will show you. All right, so first derivative test, increasing, decreasing, relative maxes, relative mins. I can find the absolutes by plugging in to find out if they're absolute, especially if I have endpoints, right? Second derivative test for concavity. What is concavity? Y'all remember learning about this? Okay. Concavity has to do with the way the function's opening, okay? We learned, y'all didn't learn concave up and concave down in like science or something? Yes. I feel like you, like a lens, if it's concave in or concave, okay. Oh, wait, I do remember. Yeah, I feel like we did. Okay, so if the curve opens down, this is concave down. And if the curve's opening up, this is concave up. Preston, did y'all already do this? I bet you did. Okay, so, and the place where it, so remember, whenever I'm increasing and decreasing, the place where I change direction is where extrema happen, right? Well, the place where I change concavity is what we call a point of inflection. And these points of inflection this is the second derivative test, happen where the second derivative equals 0 and changes signs. That's how I know my concavity is changing. So if the first derivative is positive, so here I'm concave up, and if the second derivative, did I say first derivative? I meant second. Second derivative is negative, then I'm concave down, okay? So all I'm doing is adding another sign analysis onto my already complicated sign analysis of, right? So now I'm not only finding maxes and mins, I'm also finding points of inflection to know when I'm concave up, concave down. So here's where we start getting into the curve sketching part, where if I can identify, I can already identify zeros, I can identify maxes and mins, and I can identify points of inflection, then I can really get a good picture of the graph, right? So let me show you kind of what this looks like. This is fun. Let me just show you from a graph how I would kind of I'm going to say there. somewhere around here. So looking at this, it looks like I'm concave down here. Would you agree? Concave up. That one's pretty easy. Here, notice, and I kind of labeled where my points of inflection. I kind of estimated where it looks like they would be changing. Do you see here? I don't have a max or a min, so that's not a requirement. But my concavity has changed. I'm concave down here, but as I swoop around this way, at some point here, I changed from being concave down to being concave up. So even if I knew where my maxes or mins were, I couldn't have graphed that quite as accurately without knowing where that concavity was changing there and where it was concave up. So on a derivative test, this time I'm looking at the second derivative to tell the concavity of what my function will look like. So here, because I'm concave down, and I'll usually do a little thing like this on my side instead of up down, this would be negative because I'm concave down. Here I'm concave up. This is A, B, and C. And so that would be a positive second derivative on that interval. B to C, of course, negative, and from C on, I'm positive, so I'm up. So notice it's where the second derivative is changing signs. So again, I have to show that. I have to show that it's when it equals 0 and that it's changing signs there. Does that make sense to y'all? Pretty easy. Let's do one. Get a good one. This is 22. All right, it looks like it's doing something like, only this is like really coming up through that thing. So I want to know, this is the graph of f of x. Use the graph to estimate where the derivative and the second derivative are 0, positive, and negative. Let's look at the first derivative first because that's the easiest for us. That's the one that we are the most used to. Where is the derivative equals 0? Zero. X equals 0. Where else? Somebody said over here. -1. Where else? And 1. I'm glad y'all can tell what that was supposed to be, even though my graph is way off. Why is the derivative 0 there? Those are max and mins, right? Where is the derivative, the first derivative, positive? So for positive, I'm looking for what? Intervals where it's increasing. So where is my function increasing? Is that it? 1 to infinity. Where is my first derivative decreasing? Negative infinity, -1. Where else? 0, 1. Y'all okay so far? Let's add the new stuff then. Let's look at the second derivative. I need to find my points of inflection first. So points of inflection are going to happen when my second derivative is 0, right? So when this is 0, I'm really looking for points of inflection. Where might that be happening? Well, let's go on our graph and let's just kind of look here. What is the concavity here? Up. We all agree, right? Concave up. Where does it change from being concave up to being concave down? Because I see it concave down here. So I'm going to go about, right, this is my numbering is way off and I'm really sorry. If this is at 1 and it crosses over at 2 here, I'm going to say about halfway in between here. If you can see the picture in the book, it looks a whole lot better than mine. So I'm going to say somewhere about halfway in between. I'm going to call that my point of inflection. I'm going to say that's a pretty good estimate for my point of inflection. And I'm going to say the same on the other side because it changes from concave down to concave up. So I'm going to say about here is another point of inflection. And these are only happening when concavity changes, and concavity never really changes again. Those are the only two places it looks like that it changes. So where is the second derivative 0? When x equals what? Negative 1/2 at those points, and 1/2. Where is the second derivative positive? Say it again. Negative infinity to negative 1/2. Back to exclusive. And then from what? 1/2 to infinity. How about negative? What do you think? You think you can try them, or do you want me to do another one? I have another one. Okay. Let's do one first and second derivative test all together algebraically, and then I'll shut up. Do a good one there. Yes. Oh, this is a good one. This is 38. Find all local maximum, local minimum, and all points of inflection. What are those? Either maxes or possible maxes or mins, right? Depending on what. Okay. So let's look. This time I was given the derivative, which is nice, right? So the zeros are easy to find here. Avery's exactly right. 1, 2, and 4. Well, that's really x minus 1, x minus 1. So it's just a repeated solution. All right, so let's test them. What happens if I go, well, this one's always going to be positive, right? Because I'm squaring it, so it doesn't matter. I'm really just looking at these two pieces. So if I put, let's say, negative 2 in, I get a negative times a negative, right? Which is a positive. If I put in maybe, I don't know, 1.5. 1.5 minus 2 is a negative. Am I positive again? And then between 2 and 4, positive here, but a negative there, so I'm negative. And then as I get bigger, I'm positive and positive, which is positive. So it looks like I have a max negative. 1.5 minus 2 is negative. 1.5 minus 4 is negative again. Everything, yeah. And so what I'm doing is I'm just looking, since they multiply together, all I'm worried about is the sign, not the actual value. Is, okay, so if I plug in 1.5 here, I get a negative. If I plug in 1.5 here, I get a negative, and two negatives multiply to give me a positive. All right, so I got a max at 2. I got a min at 4. Old hat, right? And again, remember, we have to say because, blah, blah, blah. But for the sake of time, I'm just going to outline the max and mins here. All right, what else? Points of inflection. What do I have to do for points of inflection? Second derivative. So I have to find the second derivative. How am I going to find the second derivative of that? I think the best thing to do, what did you say? That's what I would do. That's what I was going to say. I find it easier to multiply it out into a single polynomial and then do power rule on each one than I do to try to do product and chain, and go through, because, ooh, gross. So the hardest part looks like to me the multiplying out, but I could easily, let's see, second derivative here. I know that squared would be x squared minus 2x plus 1. And these two multiplied together would be x squared minus 4 minus 2 is minus 6 plus 8. Now I can multiply out. X to the 4th minus 6x cubed plus 8x squared minus 2x cubed plus 12x minus 16x plus x squared minus 6x plus 8. And this is not y prime, this is still the derivative, I'm just multiplying out. Minus 8x cubed. Y'all multiply it to make sure you get the same thing I do. Let's see, 21. I don't want to have made a careless mistake here. But to me, that was easier. It's easier now to find the derivative. Is that what y'all got? So the second. 4x cubed minus 24x squared plus 42x minus 22. But remember, now I'm back to my derivative test. So I'm setting it equal to 0, and I'm solving for x. If this was a calculator problem, I would most definitely um, be looking for the zeros on my calculator. Let's see. I know I can divide by 2. Is that it? I can't group it. No, I need a PRC. I don't know how else to do it. Do you know any other way to factor it and find what x equals without PRCing it? Me neither. 2, negative 12, 21, negative 11, 2, 2, negative 10, negative 10. That's possible. But it still works. Okay. So I got x minus 1. Oh, dear Lord. You've got to be kidding me. Look, it's the algebra, y'all. It's not the calculus is just second derivative equal to 0. It's the solving with the algebra that sucks. Well, now I have, okay, so I know x equals 1. There's 1 that's going to go on my little test up here. 2x squared minus 10x plus 11 equals 0. Now do you see why I said, oh, good Lord? It doesn't factor. Which, say that again? I don't think that's going to work, though. Because then you get 4x minus 10. But that's not one of the zeros. I don't think we have any choice, y'all. We might as well just do it. I know. Isn't it grand? All this to find concavity. Which is inflection and concavity. What's 100 minus 88? 12. 5, 2, let's see, 4 and 3, which is 2, so I get root 3. I did that a little bit in my head because I'm tired of writing. All right, so that's 2 more solutions. What in the heck did this tell me? Well, this told me. Yeah, so I did 12 would be 2 root 3. And then I just divided everybody by 2. Yeah. Second derivative tells me what the function itself is doing. I think I'm going to go up here to my other and put it on here so you can see it plotted kind of against this one. I had 1 was on there, right? And then I had 5 plus square root of 3 over 2, is that right? And 5 minus square root of 3 over 2. 1.5. It's gonna come about right here. Well, I was thinking if that was square root of 4, so that's going to be close to 2. 5 minus 2 is 3. 3 over 2 is, so it's going to come a little closer to 2. And then if I add it, 3.5. It's going to come a little closer to 4 over here, right? I just want you to see it plotted here against the other one so you can see that we use both derivative tests to find out what the original function is doing. All right, so I'm looking back at my derivative, which is a second derivative, which is in black right now here. And I need to know the sign when I'm less than 1. Well, that one's easy. I can do 0, right? So it's negative. So negative means it's concave down. It makes sense that there's a point of inflection here, if that's a point of inflection, because if you look, I'm changing, right, I'm changing concavity there. Okay, so let's see. Between 1 and 1.5, somewhere around in there. Great day. What's my sign look like? It is a calculator problem. Wasn't it so much fun? Okay, well then on your calculator, what's the sign? Am I fired yet? I even did it whenever I did it with without a calculator. It's positive. How about between these two? Try 2. Negative. What thing? The stove? But what I would do is I would put this in Y1, and then I would just go to my table and type values for X, right? You understand what I'm saying? Like I would type this in Y equals, and then I'd hit second graph or table, and I'd hit X equals 1.5 and see what it gave me, and then X equals, you understand? And then how about big, big, big? I'm thinking positive. Concave off. So the reason I plotted this against each other was so that you could see that I'm increasing, but my concavity changes. So it's kind of like that one we did in the beginning where there's not a max or a min, but the concavity definitely changes, right? And so that concavity change is happening at 1, where I'm going from concave down to concave up, but yet I'm still increasing the whole time. I never stop increasing, but I do change concavity. And then again, you can see your points of inflection are happening in between these increasing, decreasing, these maxes and mins, right? Because the maxes and mins are the very peak of the concavity. That's why your points of inflection are at different places. So they won't line up exactly, but they should line up kind of off if you think about that one that we first did. Does that make sense? All right, I started out easy.